Okay, so hi everyone, I'm Naomi Chevillard. I work for SolarPower Europe as a policy advisor, and I am coordinating our work stream on solar mobility.
And everyone also from Michael Villas, our policy advisor for smartEn, the other organization that is co-hosting this joint webinar.
Okay, so we will start the webinar now. All right. So I'm Naomi Chevillard, as I just told you. I'm here with Michael Villa, but we're also very, very happy to welcome our speakers with us. Jacqueline Piero, who is the Director of Policy from Nuvve. We also have with us Arina Anisie, I hope I pronounce it well, who works with IRENA, the International Renewable Energy Agency, on the topics of transport, and Nick Hubbers, who is the Head of Energy and Operation at Jedlix. Okay, so this is the overview of today's webinar. So we'll have a first introduction from my side and from smartEn to explain a bit the scope of the webinar, and then we'll have the pleasure to listen to presentations from IRENA, Jedlix, and Nuvve, who will give us a bit of context on what is smart charging and how EV integration and PV integration to the grid meet. And then we will have the opportunity to have an interactive discussion and a Q&A session during 20-ish minutes. And then we will have to close the webinar. Before we start, I just want to give you a few information, because of course this is not a regular conference, this is a webinar, online webinar. Unfortunately, you cannot ask questions directly. We will have the presentation, all the speakers will make their presentation, each one after the other. But you will have the opportunity to ask questions in the end. And how do you ask questions? You should have a small pane at the bottom of your screen in the GoToWebinar control panel. So a question button where you can send the questions. And we will then ask them to speakers. So I will ask them to speakers and moderate a bit the debate. So that's for the webinar to be easier. But feel free to ask questions during the presentations, and we will come back to them. We'll come back to them during the Q&A session. Okay, so then I suggest we start with a first welcome and context from my side, from SolarPower Europe. So 2 seconds until I can get control. Okay, so so I just wanted to give a few words. Some of us already listened to me explaining what is solar mobility, to just explain why we started at SolarPower Europe to work on solar mobility this year. So of course, our core objective is to achieve the decarbonization of the European economy. That's why we are working at SolarPower Europe to develop renewable energies. So that was the core challenge, and this will be achieved with decarbonization of the electricity sector by the development of renewable and the decarbonization of the transport sector, where electric vehicles represent a big chance. And these two sectors, so in the renewable sector, the PV, and in the transport sector, the e-mobility sector, we found out and we see that all of them meet certain challenges. In the electromobility sector, of course, you have to ensure the consumer uptake, integration of electric vehicles to the grid, ensuring that you have that we can meet the additional electricity demand, and encourage added value creation for this new technology. And in the solar sector, of course, we want to develop solar shares in the European electricity mix, including through different models like ground-mounted PV, but also self-consumption, etc. But we also need to integrate this new energy, which means further flexibilization of the energy system to increase the integration of solar. And again, in meeting all of these challenges, we need to develop innovative and competitive business models. And we need to solve these challenges to achieve our objective of decarbonization. And when we look closely at them, we realize that they're quite closely linked, and that actually from these challenges we can bring new opportunities. And opportunities solar has for electromobility. So first, it's an energy that's increasingly cheap. So that's a graph from our global market outlook that was published in May 2018, where we see that commercial PV and utility scale PV is falling costs and becomes very competitive with conventional sources of energy. Solar is also easy to integrate into urban landscapes, but also on vehicles even. And a solar PV that produces during the day can, of course, with smart systems, can match the electricity demand from vehicles. For example, a vehicle that's charging at the office or at a parking station during the day. So from there, we began to sow a lot of interest, and that's why we started the Solar Mobility Workstream. So we look at different questions that you can see on the screen: how to power electric mobility with solar, in particular through power purchase agreements. Are there synergies in the installation, operation, and maintenance? Then a look at infrastructures and vehicles, so how to integrate PV on the mobility. The value of smart charging for the integration of PV and EV. That's what we're discussing today. And retail innovation, so how to develop new PV and EV offers for the consumer. And our work stream will address all of this issue. We have organized a series of webinars. The last one was in November on how solar could power mobility. We aim at developing intelligence, so a report on these new business models. We also are going to reflect on the best regulatory practices that encourage clean mobility that's coupled with renewable and with solar in particular. And we will organize events where our aim is to bring together the automotive and solar sector. So that's it for the solar mobility workstream. I'm happy to answer your questions, and then I think I can give the floor to Michael from smartEn.
Can you hear me? Yeah. So indeed, I'm Michael Villa, Senior Policy Advisor at smartEn, and I would like to thank indeed Naomi for this introduction and briefly introduce smartEn, Smart Energy Europe. It's indeed the business organization of market players driving digital and decentralized energy resources. And for us, smart charging and electric vehicles will be the objective of a specific task force that we are going to develop throughout 2019 and to provide some specific recommendation for both the uptake of smart charging, so proper infrastructure, and electric vehicles themselves. As Naomi was saying, next slide. The Commission has a key ambition. You might know that the Commission 2 weeks ago presented its own strategy to go climate neutral by 2050, and of course the transport sectors has a key role in that. Why? Because indeed all sectors have seen emission reductions since 1990, but the transport sector instead has increased them by nearly 25%. So it's a must indeed to reduce transport emissions. So the reason is mainly due to the use of diesel and petrol as being mainly dominated which are dominating the internal combustion of engines across Europe. However, there are good news. We reach 1 million electric vehicles this year. We had a 2% market penetration that is going to double in 2020 and reach up to 63% in 2040. So in less than 15 years, 2 cars out of 3 sold in Europe will be electric. Recent data from Bloomberg New Energy Finance are saying that by 2022, 52 new battery electric vehicles models will hit the market. So indeed, there is also a move within the car industry to provide indeed electrified vehicles. Is it going to cause a stress or a problem to the electricity systems? Well, if we take in consideration that electric vehicles, if charged at home by indeed households to charge a daily distance of 30 kilometers, might increase up to 80% of the daily demand of buildings, well, it might be a problem. Indeed, full electrification of road transports will increase today's total electricity demand of approximately 20%. Therefore, we need to integrate the electrification of electric vehicles into a smart way. And that's why, indeed, electric vehicles should not be understood as problems to the grid, but as real decentralized energy resources. So, indeed, the electricity system can cope with this increase in electricity demand, specifically in the transport sectors, as we are targeting now in this webinar, only if electricity demand become flexible. So indeed, it's key that smart charging is done in a demand-side flexible way, and smart charging is indeed a smart demand management opportunity. So what does it mean? That smart charging should allow consumers to charge when electricity price conditions are more favorable, when the network is not congested, when there is indeed abundance of renewables, for example, in the system, and this is specifically the object of this webinar. And electric vehicles and the batteries in electric vehicles can also be used as technologies that enable customers to actually interact with the grid and facilitate the integration of renewables. So up to a bidirectional evolution. So in this case, smart charging will be the enabler to make electric vehicles much more competitive. So to provide users with a way to save money, or to have a new source of income, to contribute to a more flexible electricity system. So to consider electric vehicles as a real assets for the grid management, and also create new opportunities, in particular for third parties like the aggregators that can aggregate indeed the flexibility potential of the different electric vehicles. However, indeed, the legislative framework can help to enable the conditions for the uptake of smart charging for electric vehicles. One of them are listed here, and for example, is the removal of regulated prices when and in case they harm to reflect the full value of flexibility, so the real value of energy. These will allow indeed electric vehicles to adapt and their consumption on the basis of the real value of energy and the real congestion of the network. There should be the opportunity for customers to sign dynamic price contracts and data that will be key in order to adapt this consumption on the basis of the system needs to be interoperable. There should be communications standards applied to the use of these data, and these data should be accessible by third parties, so service providers that can indeed have use of the data from final customers using electric vehicles. These third parties as aggregators shall have market access, so to have the opportunity to pool this flexibility, to aggregate them, and indeed commercialize them in all electricity markets. So this access for aggregators should be also linked to the opening of all electricity markets for all decentralized energy resources, in particular storage and demand response in this specific case, and also incentivize the system operators to procure flexibility services and not just to invest in copper. And in this case, the contribution of electric vehicles as decentralized energy resource might see this as a flourishing opportunity. I will stop now and happy to maybe reply to some questions, but more interested in listening to the business cases of our guests. Thanks.
Okay, thank you, Michael, for this introduction and which set, I think, the scene and why we need to be discussing about smart charging today. So now I will move to the presentation of Arina, who worked for IRENA, the International Renewable Energy Agency. So Arina, I think you have the floor.
Hello everyone, do you hear me?
Yeah.
Yes. Hello, Naomi.
Yeah.
Hello, everyone. Yeah, thank you, Naomi, for the introduction. Let me see if I can change the slides already. Okay. So yes, my name is Arina Anisie. I work as an Associate Program Officer for Renewable Energy Innovation at IRENA Innovation and Technology Center, located in Bonn, Germany. And thank you very much for inviting me to be a speaker in this webinar. With my presentation, I would like to provide a few key insights in an upcoming IRENA publication, and part of the Innovation Outlook series focused on smart charging for electric vehicles. A little bit on the context of this study in IRENA and the link between electric vehicles and renewables, very well emphasized also by Naomi and Michael's presentation. But I will just wrap up very quickly. So IRENA studies indicates that in order to comply with climate targets, decarbonization of end-use sectors through electrification is needed, powered by renewable electricity. We see in the graph on the graph in the right that electricity demand will increase drastically from 2015 and to 2050, and this is mainly due to the electrification of other sectors. And renewables need to cover 85% of this demand. On the right side, we have the increase of electricity share in final energy use in buildings, industry, and transport sector. And if we look in the transport sector, we see that we need to increase from 2015 levels 1% of electricity share in final energy use in transport to 33% by 2050. So electric vehicles, this increase of 33% of electrification will be done largely by electric vehicles. And electric vehicles create a paradigm shift for both the transport and the power sector, enabling the decarbonization of both sectors by coupling them. What does it mean? For the power sector, electric vehicles represent mainly small batteries connected to the grid, which, if well managed, they have the potential to provide flexibility to the system. Flexibility is very important in a system with high share of variable renewable energy, such as wind and solar, whose generation is variable and uncertain. So even though in the power sector there are many other flexibility options emerging, what makes electric vehicles unique is that they are not developed to serve the power sector, but they come from another sector, the transport sector. And their development is pushed therefore differently, but their deployment could represent a great opportunity for the power system. On the other side, to decarbonize the transport sector, the electric vehicles need to be powered by renewables. So it results therefore in a win-win situation for both power and transport sector if electric vehicles are well managed. What does it mean exactly well managed? Basically smart charging. Michael already introduced this concept in his presentation. But in our study, we explained that managing the extra load of electric vehicles needs to be done smartly in order to harness this flexibility potential for electric vehicles, and even more than harnessing this flexibility potential, in order not for electric vehicles to pose an extra charge on the demand on the power system. So smart charging is basically adapting the charging cycle of electric vehicles to both the condition of the power system and users' needs, and facilitating the integration of the vehicle in the power system while meeting also the mobility needs. There are different types of smart charging, from simple time of use tariffs, which basically sends price signals to the users, and it depends entirely on their behavior, whether they want or not to respond to the prices, to more advanced smart charging that also involves automation controls. The more complex the smart charging is, the more flexibility it can provide to the grid. However, there is a trade-off that should be considered between the cost and challenges of implementing such options and the benefit that each power system can take for it. I would like to emphasize that without smart charging, what is the impact of electric vehicles that can have to the power system without smart charging? It has a limited impact on the total electricity demand, but a very high impact. It can have a very high impact on peak demand and on local distribution grids, leading to frequent congestion. Therefore, smart charging, it's very important to mitigate this impact, and it can include different pricing and technical options, from time of use pricing, as mentioned, to other direct control mechanisms. And here I will look at different options for direct control mechanisms. Basically, they have been developed for automated reaction to price signals, improving the consumer's responsiveness to prices. So the consumer will not need to check the prices and decide when to charge the electric vehicle. There are electric vehicles, but there are some automation in place that could optimize this. And there are various types of this smart charging. V1G is a unidirectional control charging. Basically, the vehicles adjust their charging levels. Or in V2G charging, vehicle to grid, the vehicle can also discharge the battery to provide back power and services to the grid. And some variations are also V2 home, vehicle to home, or vehicle to building, when the vehicle is connected behind the meter and it can help the consumer optimize its load. So there are different types of services and flexibility that EVs can provide through smart charging. On one side, there is flexibility at the system level, providing the system services like peak shaving or ancillary services. On the other side is, and maybe more impactful, there is flexibility in the local grid, providing services such as load congestion management for the DSO, distributed system operator, or even for consumers when connected behind the meter. EVs can help arbitrage, for example, between locally produced electricity, solar rooftop PV that a consumer might have, and buying electricity from the grid. Also, it can provide valuable backup to consumers. few parameters define the smart charging of electric vehicles as a flexibility option. It is important to know how long the vehicle is plugged in, the time of the day it is plugged in, where it is plugged in, and this is mostly important for the local grid, and it depends on the strengths of the grid and in this location. What equipment is available, in the sense that what charging station is in place and what capabilities it has for charging, and also the capacity of the battery of the electric vehicle, how much capacity it has. However, very important for smart charging is also the regulation and business model in place. For consumers to participate to smart charging, the benefits must be clear, and all services that they can provide to the grid, they must be remunerated accordingly. Also stacking of revenues from providing different services should be recognized and should be possible for a viable business model. In our study, we projected a possible evolution of electric vehicle flexibility by 2030 and by 2050. While today the electric vehicle penetration is generally low and smart charging appliances are not developed yet, in 2030 we foresee a higher penetration of electric vehicles, larger and more efficient batteries incorporated in the car, and more developed smart charging applications. Also, positive aspect is that the vehicle will, as today, be standing most of the time and with the battery connected and available to the grid. However, in our analysis to 2050, we foresee innovations emerging also on the e-mobility sector that will change these dynamics. Here we consider the emergence of autonomous vehicles and the sharing economy, where people will not own a car, but mobility will be seen more as a service than as a property. So therefore, the number of vehicles will decrease, and their time for being connected to the grid will also decrease, and this will affect the flexibility they could be able to provide to the grid. This is a representation where we can see graphical of how flexibility provided from a single electric vehicles is increasing by 2013. Through development of as I mentioned, smart charging applications and the higher penetration of electric vehicles. And it's followed by a decrease towards 2040, 2050, due to mobility as a service emergence and the decrease in the number of cars and decrease in the time they're available to connected to the grid to provide services. What we wanted to assess also in our study is what is actually the impact of smart charging in the energy system, both at the system level and at the local level. For assessing the impact on the system level, we modeled an extreme case system. It is a small isolated system with very high share of solar generation that I will present to you today. We have also wind generation that it will be in the report. And electric vehicles are also the only flexibility option considered in this model. So I will not focus too much on the assumption and on the model. I just wanted to send a few messages from our results. And one of them is that smart charging, both vehicle to grid and unidirectional smart charging V1G, enables to cover the EV load with a higher share of solar and contributes to reduce the yearly peak load. When electric vehicles are used as batteries, basically vehicle to grid, it facilitates the integration of solar PV in the system through reducing curtailment and at the same time reduces the marginal cost of the system. We also model the effect of mobility as a service scenario, and in this scenario, we see that electric vehicle bring a much higher load to the system and provides less battery capacity for grid services, as mentioned, and basically largely cancel out the benefits of smart charging. For illustrating the impact of EVs at the local level in the distribution system, we present few real case studies. And one of them that we found is the experience of DSO in Hamburg. Hamburg is today the city in Germany with the highest number of charging points. It has 100 charging points in households and 810 charging points public. And according to the DSO in Hamburg assessment, at 9% electric vehicles penetration level, they see that 15% of the feeders in the city will be overloaded. Therefore, one solution is to reinforce the grid, and their assessment shows that the investments rise up to 20 million euros for the grid reinforcement needed to mitigate this impact. However, the smart control solution costs only 2 million euros, and it solves the problem by decreasing simultaneity. This means by decreasing the number of electric vehicles that are charged at the same time. So basically, the DSO wants to be able to reduce the loading current for charging electric vehicle, so that to avoid this overloading the local grid. And for this solution, DSO of Hamburg partnered with Siemens, who will install 30 control units and will monitor the private charging infrastructure loads. So we see that at a 9% penetration of electric vehicles, smart solution allows grid investment savings of up to 90% in this case. In another case, we looked at Endesa, Spanish DSO, who assessed the distribution grid reinforcement costs with and without smart charging at different penetration levels of electric vehicles. And if we look at the table, for example, at 15% of electric vehicle penetration, V1G is the smart charging they assess, allows for grid investment savings for more than 1 billion euro. So substantial savings in distribution grid. I would like to end my presentation now with some high-level guidance for policymakers we provide in the report for electric vehicles deployment. First, the development of electric vehicles and renewable energy should go hand in hand and not one without the other. Therefore, targets and incentives both for transport sector for electric vehicles and power sector for renewables should be considered. Secondly, with the deployment of electric vehicles, smart charging options need to be implemented to harness the synergies with the renewable energy generation. This involves both smart charging equipment in place and also sound regulation that sends the right price incentives and value smart charging properly. And last, studies on the development of mobility as a service and its impact in long-term evolution of smart charging needs to be carried on. Also, an integrating planning of power and transport sector will be needed for the countries. This was my presentation. Thank you very much for listening, and I'm open to questions at the end. Thank you.
Thank you, Arina, for this extremely interesting presentation and also an early bird presentation of your report, because I think you're going to publish it in January. And present
yes, I would say first quarter of next year. I don't promise January, but
okay.
Yeah. So.
Okay, but anyway, yeah, so thank you. We are aware that it's very early results, so we're very grateful that you could present them to us. I think it showed well that smart charging, it's not one thing, it's a variety of technologies, but it's also a lot of benefits for the systems. But of course, we need to work on it to enable it at policy level and as well as at technical level with further improvement of technologies. But without any more transition, I will move to Nick Huber's presentation. So Nick Huber, you work in Jedlix since February 2017 after an experience in the energy sector. And you're going to present the activity of Jedlix, who provides a smart charging solution. So yeah, Jedlix is a Dutch startup active in smart charging for a few years now, and I will now give you the floor. I think you have controls.
Well, thank you very much, Naomi, for this kind introduction. So indeed, name is Nick Hubbers, and I'm leading Jedlix participation in the energy markets in Northwestern Europe. I've been asked today to explain you a bit about how our smart charging solution supports the integration of renewable energy. So let me very shortly introduce Jedlix to get to this question as soon as possible. First about Jedlix. So we are a software company that provides solutions in order to optimize the charging process of electric vehicles. We are established in 2016 and based in the Netherlands, where we have launched our commercially live smart charging service since 2017. In the coming year, we will launch our service in other countries as well, like Germany and France. And our user base is ever growing and consists out of several thousand EV drivers, mainly Tesla and Renault drivers who charge their vehicle at home. But we are also able to smart charge on more than 2,000 public charging stations through cooperation with several charge point operators. So smart charging, I think, was well explained by Michael and Arina already, but to summarize a bit, assume that you connect your car when you arrive at home. Most of the time it only needs a couple of hours to charge, but it stays connected to the grid for the whole night. If every person with an electric vehicle would like to charge his car as soon as possible, it will create a peak which needs to be filled up with additional power production coming mostly from fossil fuels, since renewable energy production is, well, uncontrollable. So we think that this is not sustainable, and instead we tune the charge process to the availability of energy matching supply and demand. Simple economics teaches that when demand is low, it's cheaper to buy electricity, so a share of the difference will be paid back to the EV driver, lowering the cost of electricity. So how does this work? Basically, we have 3 integrations to make it work. We have an integration with the car manufacturer in order to send charging commands to the car and retrieve information that we need. We have a user interface, which is a mobile application to collect the charging preferences of the EV driver and to interact with the user. And we have energy parties who offer on which we offer flexibility and to monetize it into the energy market. Let's start with the car manufacturers. So we provide 100% software-based integration, which uses the existing wireless connection of the car. This means that there's no additional hardware required, and this makes it a very lightweight and scalable solution. Currently, we're working together with Tesla, Renault, and BMW, and we expect more OEMs to join the platform soon. For the user, we are providing mobile applications. In this application, you can connect your car, you can set preferences like when are you normally leaving, and how much of the battery do we need to charge as soon as possible. This gives us all information that we need for providing the flexibility. This application we provide in our own brand, which is Jedlix, but we also have a white label solution, for example, with Renault. That is the ZE Smart Charge app provided by us. In the app, there's also possibility to connect your energy company in terms of your energy contract. If you add your energy contract, we will use our integration with the energy supplier to allow the energy supplier to buy the electricity on cheaper moments. So the electricity supplier can use the platform in order to shift from the more expensive hours, which you would normally charge, to the cheaper hours in the night. This is, for example, on the day-ahead market. But if you look more closely at prices during the day, there's much more variation in electricity prices coming from forecast errors, like there's more solar than we expected, driving prices here in the Netherlands for yesterday sometimes even below zero. Well, the energy supplier can optimize the purchasement, and a part of the savings are being transferred to us, which we share with the EV driver. This way, the user does not need to have a different price plan or a time of use tariff. It can be possible but for now, a flat tariff, and we provide the benefits back to the user. So we're now looking into supplying these balancing services during the day, independent from the energy supplier, for which we teamed up with Next Kraftwerke. Next Kraftwerke is an aggregator, maybe the largest aggregator in Europe. And through their platform, we are providing balancing services to TenneT in a 2-year pilot project starting 2019, where some of the barriers for EVs to access the balancing markets are being addressed. One of the examples is measurement. How can you prove that all these cars are delivering balancing services? One of the things that we did is that we showed that the meter inside the car is perhaps just as good as the ones that are used in the energy market processes. And we also showed that cars are perfectly able to follow real-time signals coming from the grid operator. So in short, we tuned the charging process to electricity prices, which are closely correlating to the availability of renewable electricity. But what we also see is that there's getting more real-time information available on the electricity mix. So how much solar and wind energy is produced at the moment. We think that this could even further drive down CO2 emissions if we integrate this information into our platform. This information is coming from national sources or by companies who are providing this information commercially. I've showed a couple of providers here in this slide. And one of the challenges that we have in using this information is that, of course, we think it's valuable to save up to 25% of carbon emissions by steering the charging process based on this information. But how can we monetize this? It's a bit hard to find a business model at the moment for CO2 savings. We are hoping to that this will change in the future, and I'm happy to discuss with the participants what the possibilities are over here. We are also looking at local production. For example, if you have solar panels on your roof, can you then use it to optimize the charging process? For now, our current target group is basically charging over the night, which is not really suitable for solar charging. But as Naomi explained, people are more starting to charge at offices, public charging stations, or perhaps we see homes with storage in the future. So we think it will change, and we will open up these services as soon as it's commercially viable for us. Also, one of the challenges that we see is that with current remuneration for solar production, it's better to supply the energy back to the grid and charge it then later at lower tariffs. And I'm curious how my colleagues here in the presentation are looking at this and how this might change in the future. Also, I would like to raise a question: is it better to optimize locally, or should we focus on the national electricity mix? Well, this is more or less the end of my presentation. In the end, we want to deliver on the sustainable promise of electric vehicles, which is making mobility more clean and more affordable. So I'm looking to more of your questions and discussion. And if you are interested in collaboration, I've added my contact details over here in the presentation, which will be shared with you. Thank you.
Thank you, Nick, for this presentation and for sharing a bit what you do and what you're looking at Jedlix. So now we will move to another model of smart charging. As I said, smart charging, it's not one thing, it's a different thing. So we will now welcome Jacqueline Piero, who is Director of Policy of Nuvve. Which are particularly welcome because you're calling in from San Diego in the US. I hope it's not too early for you. So Nuvve is commercializing vehicle-to-grid solutions, so bidirectional charging station and V2G solutions. And you are a US-based company, but now more and more active in Europe. With that, I will give you the floor. I think you have the control.
Hi. Okay. Yes. Testing if I do have control. It looks like it. Okay. There we go. That's me. Right. So as the introduction said, Nuvve is an energy services company, and we concentrate on behind the meter kilowatt scale resources, and that can include solar and solar PV and stationary storage, but we're primarily interested in electric vehicles just because the opportunity there is going to be so significant. But so I was asked to speak specifically about a particular project that my company is doing. There we go. In California, actually, to explore how EVs. Why is it going? It looks like it's on.
Can you use your wait? We're going to pass the slides.
Sorry.
It seems that your presentation has.
It went on automatic.
Yes.
Can you take control and stop it?
Wait.
Or we could just do, I could go turbo through it.
I think it will be better now.
Okay. Okay. Thank you. So, do I have control of it?
You do.
I do. Okay. Right. So, starting over, as we have participated in frequency response markets in Tenet, in PJM. It's doing it again in California as well, and in Denmark. And we have also done a fair amount of behind the meter optimization. I don't know why it won't stop.
It's a live accident. It's fine. Okay.
Okay. But they're figuring this out. We are also looking forward to see exactly how EVs will be fully integrated into the grid beyond just a few services or time of use. And is it possible for me to click back on the back button? Let's see. It looks like it. Okay. Wow. Okay. And one of the projects that we're working on is called the INVENT project, with which stands for Intelligent Vehicle Integration, essentially. This is going on in California at the University of California, San Diego. And it is exploring the match between EVs and solar output. And the overall, this is the slide that I mean to be on now. So this is good. The overall service evaluation is looking at distribution level, demand response events, at behind the meter optimization, looking at multi-unit dwelling applications, as well as just one single facilities. at being in the frequency regulation market as a simulation, because it's a 2-year process to get a new entity into the regulation market there. So we're simulating it for that project. And then also adding on the solar element to try and fully contextualize it with the rest of the services that an EV could potentially be participating in. And okay, here we go. So the University of California, San Diego is actually a microgrid, and it provides most of its own electricity needs, its heating and its cooling. And they are now working with EVs to see how those actually fit into this grid. Here we go. So we are working with multiple types of cars with Mitsubishi, Nissan, Tesla, Chevrolet, Smart, and BMW, and with 2 types of chargers. They're AC chargers and DC chargers. Right now on the actual campus, I think there's less than 20. But then as we move out and start working around the state in the different DSOs, we're going to have more like 50 actually. And it's going to be partly dedicated to introducing to the DSO how EVs can actually be working on their systems, and sort of change that perception at the DSO level from EVs as a problem to be solved or controlled, and take it to a resource that the DSO can actually be using to balance their grid in various ways. And so one of the actually most complicated aspects of this is that we are working, we are working with both unidirectional, just smart charging, and then also bidirectional charging. And the reason that this makes a difference is that to understand what the capacity within an aggregation platform would be when you consider the different capabilities and the different use cases that have to arise based on this one capability. Are you just modulating your rate of charge, or are you discharging, is actually going to be one of the most interesting outcomes of this project, I think. So we have a few different use cases that we're looking at, and there's just workplace charging. There is actually a fleet of Leafs that is used overnight to shuttle kids around from place to place when it's not necessarily safe to be walking around. There is an actual on-campus fleet of cars that are used, and then there are people who are just driving to work. And so when will these cars actually be plugged in? When will they be needed? How big a battery do they have? So for the V2G solar match question, we're looking at 4 different aspects of solar PV output and EV use cases. There's the normal time of use, which isn't necessarily a solar thing, but it's sort of the base constraint within which we know that we'll have to be working. There's just time shifting energy that is being produced during the middle of the day when it's not necessarily a peak usage time. There's capacity firming that there are 2 different versions of that I'll explain in a minute. And then there's actual ramping services. And it's important to actually look at all of these as one picture to understand, as one of the previous panelists was saying, what value are we going to look for in EVs? Is it going to be working at the co-located, the co-sited level and optimizing there? Is it going to be a system service? Does it need to be a mix of the two? Where's the value? Are there different use cases that are actually more appropriate for the different values? Does this actually have implications for policies that would encourage charging to be done in one location as opposed to another? And how do you actually unlock that value to incentivize users to participate in the related service? So every country that has any real solar integration will have a duck curve of some sort, but California has an especially pronounced duck curve. And this means that because it has a very long north-south grid, the sun is going to be hitting pretty much every solar panel at about the same time, and it's going to be stopping hitting every solar panel at about the same time. And so at the during the middle of the day, you're going to have a very low apparent demand, and then toward the end of the day, as the solar PV stops producing, you'll actually have a 13 gigawatt ramp requirement in just 3 hours. This is incredibly expensive, and it's incredibly stressful on the generation assets that are needing to ramp up. Add to that all new residences in California will be required to have solar PV on their rooftops, and you've got quite a situation developing. For that reason, the DSOs in California have generally shifted their peak time of use rate hours from the middle of the day towards the end of the day when solar stops producing. This is specifically to deal with the solar situation, because they want to actually make sure that there is not a new peak that is actually generated, or a higher peak because it's still hot. People are still wanting to use air conditioning in California at that point. They may come home and charge their cars, and the state is trying to avoid that happening as much as possible. So there is already a price signal out there that is related to solar production, but in general, we know that this is just a first step. And the TSO for California, CAISO, is exploring market options to actually bring more nuance and more direction to not simply shift the peak even later, for instance. So, here we go. As I was saying, there were two different, call it manifestations of capacity firming that we want to examine over the next year in the study that we're doing in California. The first is the basic idea that this chart shows, which is simply you're trying to even out your usage. And this might, if you were at a house, be manifesting itself as shooting for a net zero load, meaning if you would simply have a switch that essentially said, if the solar that we're producing is more than the demand of the house and we would be exporting, then we will charge the battery, we will charge the car. If the solar is producing less than the demand of the house and we would be importing, then we would discharge the battery. This is one way of looking at how you could actually be working with each distributed solar resource and trying to stop voltage issues and line loading issues before they begin. But when you go to the industrial level, then we get into the PPA idea that had been mentioned before, where you would actually have industrial, and we've had some talks about this and trying to figure out how it would work. You have industrial solar farms or wind farms that actually need capacity firming services to fill the difference between their forecasts and their output, so they don't get dinged with penalty, and they can actually contract with a distributed resource like 10,000 cars to be evening out their own usage. And that may look like this graph here, or I think it might, or it may look like this one here, where you can see the dotted line is all energy that the sun is could potentially beam down, whereas the GHI is actually the radiance that's actually hitting at that time. And we would decide when do when do we want to charge? Do we actually want to charge at that ramp time? Do we want to charge at an increasing rate as the actual output of the panel is increasing to match that? Do we want to fill in maybe this gap where there might be a little bit of variation between the predicted output and the actual output? And what is the value of that to a solar company, for instance? And here we have the duck curve. Whoops. At a system level, what I was just describing is, so we've looked at capacity firming and ramping to some extent at the house level, at the industrial level, and now we look at it at the system level. Here we have the California duck curve, and there has been an acceleration beyond what anyone expected. We've already reached the 2020 level of output and daily change in 2016. So no one's sure exactly where it's going from here, but this belly of the duck and the neck of the duck are where there is real value to be seen from EVs. And so if we were able to charge during the day to actually increase the net demand, and then discharge as the neck of the duck is starting to kick in to flatten out that ramp rate just a bit to give other generators time to kick in, there's huge value there to the system. A Lawrence Berkeley National Lab study from last year actually estimated that if you could just do smart charging and do those two functions that I was saying, fill the belly of the duck, flatten the neck of the duck, a one-way charging car that was doing that, or the one-way charging fleet that was doing that, if it was the California fleet that is the target, which is 1.5 million EVs at the time, then that would be worth $1.45 to $1.75 billion in the equivalent installed stationary batteries that would be necessary to do that. But if those cars were bidirectional, that same fleet of cars, the value's 9 times the value of just smart charging when it comes to equivalent stationary batteries that would need to be installed to have that impact on the duck curve. So this is a huge value at the system level. But right now, the only incentive is for our cars to be doing that is about 30 cents per kilowatt hour in time of use arbitrage. If you were working with solar that you were shifting to a different peak, might be 68 cents. And then a demand charge if you're actually at a commercial and industrial site. But I would put forward that this value should actually be acknowledged and passed on in some way. We need to actually be able to make smart decisions about subsidies. For instance, this case that I'm showing clearly shows that workplace charging will be of far more use at the system level than home charging. And that is a decision that can be made by regulators. It can be made by government when it comes to actually incentivizing installations. And that can be done through rates. It can be done through subsidies. But it can also be done through making sure that those value streams are realized, designing metering and regulatory constraints around behind the meter participation in external markets and value streams so that cars are actually allowed to do this. You can see the value, you can see the place that they should have in this system, but they probably can't take that place right now. And so what we're hoping to do with this study at the University of San Diego is to actually show what are the use cases that are of the highest value to the system if we want to actually go for real CO2 reduction goals. Where do cars need to sit in that system? And rather than just dealing with them as they come, we should choose and we should push them in the direction that we want them to go. So that's it.
Okay, Jackie, thanks a lot for this presentation. That was very interesting to see where Nuvve has looked in the development of smart charging technologies, and also in particular in the synergies with solar generation, in particular in California. That was a good example. And again, sorry for the inconveniences of the presentation. That's issues of webinars, but it's also good to have you, even though you're very far from us in Brussels. Okay, so thank you all for your presentation. We will now move to an interactive discussion and question and answers. So let me check. There's so a question about I've heard of utilities offering EV smart charging services to consumers as well. Which way is this going to be rolled out, from service providers like Jedlix or from utilities directly? Do utilities need partners like Jedlix to roll this out? So yeah, what is the value chain of the provision of smart charging services? If I understand you correctly, will it kick out utilities? What will be the role of utilities? Maybe Nick, you want to answer? Arina, Jackie?
Sure. Let me try to kick off this first question. Thanks for the question, first of all. Yeah, so kicking out utilities. As of now, I see that there's still an important task for utilities in this value chain, since they have the let's say balance responsibility of the end user. In some markets, you see like independent aggregation coming up, which allows smart charging or optimized charging through balancing service providers. This could potentially create value without the need of a balancing responsible party being involved. But I see that these markets opening up could take some time. I'm not sure how this is the case in North America. Perhaps my colleague from Nuvve can tell you something about that. But for Europe, I foresee for the upcoming period that we need to partner with these utilities to reach the end user.
May I add something?
Yes, please.
Sure.
Okay. Yeah, from my point of view, there are kind of complementary things. These energy as a service providers are in a way helping the utilities. What is the utility? At the end of the day, main utility is the DSO actually. And the impact of the electric vehicles, it's highly on the grid congestions and on the DSO lines. So we have seen in the case study with Hamburg that I presented in the DSO in Hamburg through an interview that because they are restricted, as a DSO, they are restricted to any business model and interaction with the customer. Their role is just to transmit the electricity to end user. They introduced this smart charging, smart control without having. So they choose to control electric vehicles that are connected to the grid, but there is no benefit for the end user because the retailers doesn't offer this benefit. So an energy as a service I see as retailers or small other companies that can capture the benefits for the consumer and like combine these two services while providing also services to the DSO and capturing and recompensating the users that are willing to provide the services. So I don't see how the utilities will be kicked out, but rather that they will be helped by these energy service providers for this grid.
Okay, so new actors and at the same time cooperation with traditional.
I have something to add as well. So Nuvve is actually partnering with EDF in France and EDFE in the UK, but also Belgium, Italy, and so sorry, those are the three. And it's particularly to run through their aggregation and trading platform. And it's turning out to be a good match because energy retailers in particular, if they own generation, they may be used to controlling maybe 10 assets. And if they are looking to get into the smart charging, V2G, just highly distributed generation space, this would increase their controlled nodes by 5, 6 orders of magnitude. They may have 10,000, 100,000, a million different very small, quote, generators that they would be working with. And we're finding that they do want to be in that space, but are more interested in that large aggregate sum that we can hand them, the capacity that we can forecast and offer them, rather than wanting to individually control each asset. When it comes to the distribution network operators, they are more concerned about destabilization of their grids and, as Arina was saying, looking to control charging levers or have some kind of a kill switch. And that doesn't seem to play that popular with EV owners, just because, particularly if they're not being compensated in any way, it actually makes people feel like they don't fully own the vehicle. They can't fully use the vehicle. So there's some work to be done there on determining who is best and how to integrate vehicles.
Okay, yeah, I think that's a big issue, how DSOs will create values out of these new services, this potential of services that EVs can offer. Maybe so another question from Xavier Moreau to Irina, just to come back to one of your slides. He was asking about what SRMC stood for. So it's in slide 34.
Okay, it stands for short-run marginal cost. It's the marginal cost of the system, basically modeled. which it's much lower when we see that we use electric vehicles as batteries for the grid, basically. So you can arbitrage a lot and use a lot of solar PV in the grid to cover the demand. However, I want to mention that a caveat of the modeling is that considers these batteries for free for the system. So it doesn't take into account the cost of the battery, the degradation cost, and all this. So maybe it's a bit too low in this modeling exercise. But however, yeah, this is the idea, short-term marginal cost. I should put it there clearly.
Okay, yeah. Otherwise, I think it will be in your report when published.
More details.
And another question, maybe a bit linked to the fact of the idea of considering the cost of the batteries. So we have a question from Lene Oje. In what way have the case studies in Europe by IRENA and California considered the reduced lifespan of the batteries, and what does it mean for the EV owner?
Well, yeah, as I mentioned in the report, we consider in the narrative we mention about this, and we look at this aspect. However, in the specific modeling exercise, the modeling exercise has few caveats, and this is one of them actually. The degradation of the battery is not considered, and that's why the short-run marginal cost for the situation for the scenario in which electric vehicles are used basically as free batteries for the power system, it decreases so much. But in the report, in the narrative, we mention clearly what are the disadvantages of this and how the batteries can be then used as second life batteries if they are too degraded for the battery to be used in the electric vehicles. It can be connected to the grid and used as for second life batteries and can still receive some revenue for that. So yeah, I don't know if I answered, but in the model it's not considered.
Yeah, no, I think you did.
I can speak to that a bit actually, if that's all right. So Nuvve actually has been working on assessing what degradation could be happening based on various use patterns. And this has been both monitoring state of health of all of the batteries in every car that we work with. And we've been actually doing frequency regulation in Denmark for 2 years using the same set of cars. And Denmark actually has the wildest frequency of anywhere in the world that we've found. So we actually consider it for that particular application to be the most extreme one, extreme use case. And we actually haven't seen any real accelerated degradation of the battery. And we're using the data that we're getting, we're giving it to OEMs to actually allow them to put it through their degradation models to see what would the lifetime degradation of the battery given these energy throughputs be. But that's just one application. So.
Okay, yeah, indeed, that's. I think that's very interesting. Because that's a concern that we hear a lot. The impact, in particular, of vehicle to grid on the battery lifetime and yeah, quality. So, no, very important.
We're actually the OEMs in general are starting to understand that they will need to have an accreditation procedure essentially for any aggregator that would want to use their cars, particularly for bidirectional energy flow, to actually qualify to be allowed to use those cars in that way. And then there needs to be auditability, second by second auditability, which is a lot of data, but that's what OEMs will need to understand. How is this car being used? Is it having any real impact on the battery life? As soon as we've actually impacted the battery life in any measurable way, this is no longer actually a good business model. We can't shorten the life of the most expensive part of the car to make some money. It has to be a reasonable trade-off.
Okay, yeah, no, that's clear. Okay, I'll move on to another question from Christelle Verstraeten. Has any of the panelists looked into the potential of charging electric fleets? While typically these will be charged overnight, so without solar energy, this will represent, in order of magnitude, a lot of vehicles and size of batteries, and therefore could represent a quite large impact on the grid. Yeah, is it something like the fleet type of consumer? Has this been considered by any of you, maybe Nick and Jackie?
Yes. So it also depends on what you define as a fleet. As of now, we also have a, let's say, fleet of electric vehicles that we use. But if you look at it, for example, in a shared fleet, so a car sharing fleet, for example, this is something that we are looking into, and I can already mention that we will announce a project where we're going to test more on how to optimize the charging process of our shared fleet, where you miss some kind of information on direct information on usage, but which you can get out of user behavior and other kind of data. So I think it has a lot of potential. We are looking into it, and especially in the future, we see more car sharing. There are announced in Europe in every major city. This could be potentially bring a lot on the smart charging.
Yeah, we have absolutely worked with fleets, and we have a service fleet that is used by a utility. We also have a fleet that goes around and services bus stops, for instance. And yes, that's absolutely true. They mainly operate during the day. And so what we've found is they do come back earlier than you might expect. They may actually do their duty cycle from like 7 a.m. to 3 p.m. So there may actually be a bit of recharge that can get done while there's still a solar resource. They come back for lunch and can get a bit of top off. But the value that we see in general is more to do with honestly frequency regulation, just because often the value of that is higher overnight when there are less generators turned on to actually be working in that arena. Is it optimizing solar? No, but is it actually finding the best niche to put these in on the grid? I think so.
Thank you, Nick and Jackie, for your reply. Arina, if you want to react.
Yeah, no, Nick and Jacqueline answers were very comprehensive. I may just add, yeah, that we also looked at this through the perspective of, in the scenario of mobility as a service. So basically when car will be no property, people will not own the car, but they will just share the service of mobility, and therefore the cars will be used extensively during the day and have yeah, charging hubs that will probably be used during the night. And obviously the synergies with solar PV, solar energy, it's not so obvious in this sense, but there are still some synergies in the sense of if there might be some charging. So these cars would need then fast charging. They will not be able to be standing charging for hours. So fast charging doesn't allow for very smart charging because you need to charge the car automatically. But in the same time, you can combine a fast charging station with a battery storage and a solar PV generation. So to reduce the need for reinforcement the grid and to charge the battery, the stationary battery from the sun, and then to discharge it in the battery of the car. Regarding the fleet and the charging hubs in the night, probably there will be more synergies with the wind that blows during the night and there is not enough demand, and this could, in some context and some systems, be a high benefit. And also the location maybe of these charging hubs is something that we look at. It's very important that they are located in the same time close to the city, so to serve the city and the population, but also strategically connected to the distribution grid, to the grid, so it doesn't, where the grid is stronger in this sense, and it doesn't pose a very high charge that will lead in congestions.
Arina makes a good point that the use cases are so variable that the charging profile and the requirements for the grid at that location will be bespoke in a lot of ways. You know, you could end up just having a level 1 charger that is sufficient to actually fulfill the needs of some fleets because they just don't drive that much, and you can be trickle charging overnight, or you may need very fast charging. It will just depend. So there's going to be no just cookie cutter solution for this, I don't think.
Yeah, indeed. I think this is that's why I think we're going to follow very closely the project that you announced, Nick, at Jedlix, because that's one of the key conclusion of the IRENA's report. I think what will be the impact of the mobility as a service cases on the added value of EV flexibility. But just if I may add, one of the one remarks that was made at our last webinar pointed out at the added value of office charging stations, where you have people charging during the day, and again a large fleet of vehicles. So it represents a large potential for the grid, but also does daytime charging, so for vehicles, and also was mentioned the potential of park and ride, so a station where people park their car before taking and using the public transport systems. I see we're running out of time, but maybe a last question about whether the participants have any evidence that consumers want to charge on solar, and why is it to be green, independent from utilities, or for reasons of cost? So maybe if you have anything to reply to that, may I ask you, dear speakers, to do it shortly, and then we will close the session. Okay, so otherwise I have an answer, because I'm working on this solar mobility work stream for a few months now, and we see it's a mix of everything. You have consumers who want to be more independent, to invest in their own energy, so that's the case of self-consumption. But you have also what's driving, for example, industrial or commercial self-consumption. It's clearly costs. So because consumers get benefits from charging on solar from their own solar after a while, of course, after a certain payback period. Then the incentive of being green is also a driver for investing into a solar charging solution. But I think it's not going to be, I mean, it's a driver for investing in such solution, but it should be, I mean, it could be also an obligation, or at least that there is clear public incentive to do that. For instance, in particular in public charging stations. And then, yeah, costs. That's also what we saw from, in particular in public transport, having charging from a utility scale through a PPA without subsidies. It has been, we have already cases where it's cheaper to charge on solar than through the electricity grid. So a variety of reasons, and that's what we're going to investigate in this next month. So it's a perfect transition for me to encourage you to follow us in this solar mobility webinar. I think it was very interesting, all the presentations that were made and all the challenges that were pointed out. We could have discussed even more widely on different topics, in particular, the access to markets and the development of local flexibility markets. That's things that are very interesting and on which we're working even in the solar sector. But I will close here. I will thank very warmly our speakers for being present for this session and for this very, very interesting presentation. So, of course, with smartEn, who hosted the webinar with us today. We will continue working on that, and we will let you know when we organize our next webinar. But I also take the occasion to let you know that SolarPower Europe organizes a SolarPower Summit. So it's the association summit in March in Brussels, where we will have a session on electric mobility and clean mobility and solar. So that will be an occasion to continue discussing on this topic and also network with our members who are going to attend this webinar. So the registration are opened, and you can already register and contact me, of course, if you need more information. So with that, I will wish you all a sunny day and look forward to have you during our next webinar.